Hello, in this session we will discuss about reaction Gibbs energy, reaction enthalpy and temperature. What are the relation between reaction Gibbs energy at standard state, reaction enthalpy at standard state and temperature. The effect of temperature on chemical equilibrium is determined by reaction enthalpy at standard state. The expression is known as Van't Hoff equation. This Van't Hoff equation is derived from Gibbs-Helmholtz equation. First, I will quickly go through the derivation of Gibbs-Helmholtz equation, then we will discuss Van't Hoff equation. So, the basic definition of Gibbs energy is G is equal to H minus Ts, where H is the enthalpy and S is the entropy of the system. At constant pressure and at constant amount of species or constant number of moles, when there is the number of moles in the system is not undergoing any change, then we can write, under such a condition we can write partial Gibbs energy over temperature at constant pressure and number of moles of other species is equal to negative entropy minus S. So if I substitute this entropy expression in this Gibbs energy formula, what I will get? G is equal to H plus T partial free energy, partial Gibbs energy over temperature at constant pressure and number of moles. So I'll name this equation as equation 50. Now before using this equation 50, let's derive one more thing. Let's differentiate G over T with respect to temperature at constant pressure and constant amount of species. Constant amount of species means number of moles of all the other species remaining constant. Again I am repeating, I am differentiating G over T with respect to T at constant P and number of moles of other species. What I will get if I do that? Minus G by T square plus 1 over T partial Gibbs energy over T at constant pressure and number of moles. So in this equation 51, here instead of G, I will substitute the expression for Gibbs energy from equation 50. Again I am repeating, I will substitute the expression for Gibbs energy from equation 50 in equation 51. So here in this G I will substitute this expression. What I will get if I do that? The left hand LHS side of the equation remains same, the left hand side remains same. Then here first enthalpy, so this will be negative of enthalpy by T square, enthalpy by T square. Then the second term of free energy expression, Gibbs energy expression, so it will be negative 1 by T. This T and T square, 1 T cancels out, this T cancels out, so 1 by T partial free energy over temperature at constant pressure and number of moles, and the second term remains same. Now this negative term and positive term will cancel out. So what I will get? This second term and third term cancels out. So if I rearrange this the remaining terms, I will get enthalpy is equal to minus T square partial differentiation with respect to T for G by T. For finite change, I will get delta H is equal to minus T square partial differentiation delta G by T. The same for finite change at the standard state, I will get delta H0 is equal to minus T square total its differentiation, normal differentiation delta G0 by T. Now at standard state it is not needed to mention the partial differentiation because the pressure is constant already. At standard state the pressure is 1 atmosphere or 1 bar. So there is only one variable, that is the number of moles of species, different species present. So there is no need to mention partial derivative, we can represent with normal derivative. Now this is equation 52 is called Gibbs-Helmholtz equation. Again Gibbs-Helmholtz equation expresses a relation between reaction Gibbs energy at standard state with reaction enthalpy at standard state. So as I mentioned, equation 52 is known as Gibbs-Helmholtz equation. Using equation 52 we can determine the Gibbs energy of reaction of a process as a function of temperature. the enthalpy change is general. If we know enthalpy change, we can find out the change in Gibbs energy as a function of temperature, and generally the enthalpy change is calculated using calorimeter, or from spectroscopic data also we can find out the enthalpy change value, and that depends on the situation, what is the nature of experiment we are performing. So this was all about Gibbs-Helmholtz equation, but our aim was to determine Van't Hoff equation. So as we know, at equilibrium, at chemical equilibrium, the reaction Gibbs energy at standard state is equal to RT ln K. K is the equilibrium constant. So if we substitute this this delta G0 value in the Gibbs-Helmholtz equation, this is the Gibbs-Helmholtz equation, and in place of delta G0 or reaction Gibbs energy at standard state, I will substitute minus RT ln K. What I am getting? I will get reaction Gibbs energy, so reaction enthalpy at standard state is equal to RT square d by dt ln K. If I rearrange that, I will get d ln K by dt is equal to reaction enthalpy at standard state over RT square. This equation 53 is known as Van't Hoff equation. What it says? It says the variation of equilibrium constant with respect to the reaction enthalpy at standard state. Again I am repeating, the Van't Hoff equation relates the equilibrium constant and reaction enthalpy at standard state as a function of temperature. So this is all about Van't Hoff equation, but let's try to understand all these parameters, that is the reaction Gibbs energy at standard state, reaction enthalpy at standard state, and reaction entropy at standard state. To understand these three parameters, let's draw a graph. So to draw a graph, we can say that the reaction Gibbs energy at standard state is equal to minus RT ln K, which is further is equal to delta R H0 minus T delta R S0. So the reaction Gibbs energy at standard state is equal to reaction Gibbs enthalpy at standard state minus temperature into reaction entropy at standard state, which is further equal to minus RT ln K at equilibrium state actually. So if we rearrange, what we will get? Ln K is equal to delta R H0 by RT plus delta R S0 by R. Now this can be assumed to be a straight line equation, y is equal to mx plus c, in the form of y is equal to mx plus c. So what is my y here? The y axis will be ln K. So mx, what will be my x axis? The independent variable, that will be 1 by t. 1 by t. So what will be the slope? Minus delta R H0 by R. And what will be the c-intercept? Delta R S0 by R. So if I draw a graph between ln K and 1 by t, if I draw a graph between ln K and 1 by t, I'll get a straight line with negative slope. What will be my slope? My slope will be reaction enthalpy at standard state over R. And what will be my intercept? My intercept will be reaction entropy at standard state over R. So this is a relation of what? Equilibrium constant, reaction enthalpy at standard state, and reaction entropy at standard state. And we represented those relation in form of a graphical expression as well. Now the reaction entropy at standard state is represented as sum of coefficients of the reactants and products and molar entropy at the standard state. What it means? It means the molar entropies of products minus molar entropies of reactants. Both reactant and products multiplied with their respective stoichiometric numbers. So with this we'll discuss some special cases. So we have discussed Van't Hoff equation. So we'll see how that Van't Hoff equation helps in understanding the variation of reaction enthalpy at standard state with change in temperature. Again I am repeating, from the Van't Hoff equation we'll try to understand how the reaction enthalpy at standard state changes with temperature. Suppose we are assuming that the reaction enthalpy is independent of temperature. The reaction enthalpy is independent of temperature. So what will be the Van't Hoff equation look like? Again I am going to my Van't Hoff equation. This was my Van't Hoff equation. So if I take in limits, two temperature limits, and I am assuming that the reaction enthalpy at standard state is independent of temperature, then what will happen? If the initial temperature is T1 and final temperature is T2 and the initial equilibrium constant is K1 and final equilibrium constant is K2, then I will get ln K2 over K1 is equal to delta R H0 by R, product of T2 minus T1 by T1 into T. This is simple integration of Van't Hoff equation, so that we can obtain the relation between equilibrium constant and temperature. Again, to obtain this equation 55, we have assumed that the reaction enthalpy at standard state is independent of temperature. Only when the reaction enthalpy is independent of temperature, then only this integrated form of equation of Van't Hoff relation can be obtained. Now suppose our assumption is correct, that is the reaction enthalpy at standard state is independent of temperature, then the reaction heat capacity at constant pressure, at standard state will be also 0, because from thermodynamics we know that dH is equal to Cp dt. So if the reaction enthalpy is independent of temperature, the reaction enthalpy is independent of temperature, then the reaction heat capacity at constant pressure will also be is equal to 0. Now if the reaction heat capacity at standard state is equal to 0, then reaction entropy at standard state will be also independent of temperature, because from third law of thermodynamics we know the relation between the reaction entropy and reaction heat capacity at constant pressure. So these are the consequences of assuming that the reaction enthalpy at standard state is independent of temperature. Again I am repeating, if the reaction enthalpy at standard state is independent of temperature, then we will get an equation of type 55, which is an integrated form of Van't Hoff equation. It says the variation of equilibrium constant with varying temperature, or at two different temperatures we can obtain the equilibrium constant using the normal Van't Hoff equation, provided that the reaction enthalpy is constant. This is case 1. Now what is the case 2? Actually in case 2 we have assumed that reaction enthalpy and reaction entropy depend upon temperature, and actually they depend upon temperature. Case 1 was the more simple assumption, but in actual practice the reaction enthalpy and reaction entropy both depend upon temperature. And what is the relation of their dependence on temperature? The reaction enthalpy is dependent on temperature with respect as shown in equation 56, and the reaction entropy is dependent upon temperature as shown in equation 57. Both equation 56 and 57 involves a term called heat capacity at constant pressure. Again I am repeating, both reaction enthalpy and reaction entropy as a function of temperature further depend upon heat capacity at constant pressure. Now how I arrived at equation 56 and 57? Actually I arrived from 56. The equation 56 is derived from 58. This is extra information, we can directly use that. But how this equation 56, or how the reaction enthalpy at any desired temperature is obtained, that the equation 56 is essentially obtained from this equation 58, which says the enthalpy of formation is equal to the enthalpy of reaction at 298 Kelvin at any temperature. The enthalpy of formation is given as enthalpy of reaction at 298 Kelvin plus CPdT. Similarly, the entropy is given as the molar entropy is given as molar entropy at any temperature is given as the molar entropy at 298 Kelvin plus integration of Cp over T dt. From these two basic thermodynamic equation, we obtained equation 56 and 57. Again, what are equation 56 and 57? Equation 56 shows the relationship of reaction enthalpy at standard state at any temperature, at any desired temperature. We are taking a case when the enthalpy, the reaction enthalpy and reaction entropy are dependent upon temperature. So equation 56 and 57 shows that, and they are derived from 58 and 59 following these two assumptions. I will not go into detail of this. These 58 and 59 are obtained in thermodynamic lectures, so I will not go into the details of 58 and 59. We will directly consider equation 56 and 57. Again, the heat capacity at constant pressure is also dependent on temperature, and the molar heat capacity is expressed as a power series and temperature, and that is given as alpha plus beta T plus gamma T square plus delta TQ. As I said, dH is equal to CPdT. So if for two different temperatures T1 and T2, it will be alpha T2 minus T1 plus beta by 2 T2 square minus T1 square plus gamma by 3 T2Q minus T1Q. So this is the expression for heat capacity as a function of temperature. So I will not go to this much details of this extra information. We'll simply use the case that the reaction enthalpy is dependent on temperature and reaction entropy is dependent on temperature, and the expressions are given as equation 56 and 57. Again, both of them are dependent on temperature as a function of heat capacity at constant pressure. So I'll use equation 56 and 57 just now. So let us substitute equation 56. What was 56? The 56 was temperature dependence of reaction enthalpy. What was 57? Equation 57, temperature dependence of reaction entropy. So if I substitute both the temperature dependent expressions in delta G0 is equal to delta H0 minus T delta S0. So what I'll get? Again, I'll substitute equation 56 in place of delta R H0 and equation 57 in place of delta R S0. So if I substitute delta R H0, what I'll get? Delta R H0 298 Kelvin plus integration delta Cp dt. These first two terms are for delta R H0. Then the third and fourth terms are for delta R S0. So if I rearrange them, the first term remains same and I bring back the third term to the second term. So this first and second term becomes delta R G0, or reaction gives energy at standard state at 298 Kelvin. Okay, so this is delta R G0 for standard state at 298 Kelvin. So plus the remaining terms are there. So now I'll divide them by minus 1 by RT. I divide all the expressions, both left hand side and right hand side expressions, by 1 by RT. I have done that simply, there is no extra step here. Then what I got? Again, delta R G0 is equal to minus RT ln KT. Delta R G0 is equal to minus RT ln K. So minus vanishes and it is plus RT ln KT by RT. Similarly here, delta R G0 at 298 Kelvin is equal to RT ln K. Delta R G0 is RT ln K, but the temperature is fixed here. So R, instead of temperature, I am writing 298 ln K 298 by RT. The remaining, the other third and fourth terms are as such. So if RT cancels out, what I'll get? ln K is a function of temperature is equal to 298 by temperature, the desired temperature, any desired temperature or any working temperature. ln K at 298 Kelvin minus 1 by RT Cp dt plus 1 by R delta Cp by T over dt. So here we can use this expression. We can use this expression, final expression, to calculate ln K. But the calculation of ln K using this expression is not so straightforward. Again, I am repeating, this is a special case 2. Here we have assumed that reaction enthalpy at standard state and reaction entropy at standard state is dependent on temperature, and further they are dependent on temperature and there is a function of heat capacity at constant pressure. So this heat capacity at constant pressure term is also appearing here. Now this heat capacity at constant pressure is also is a function of temperature, and that is represented by a power series in form of T we have just discussed. So to solve this equation, the solution of this equation is complicated. To solve this equation, generally mathematical programs are used. So we have discussed two cases. In the first case, the reaction enthalpy was independent of temperature, where we can easily find out ln K value. In this case, reaction enthalpy was independent of temperature, so easily we could find out the equilibrium constant expression using just an integration. We could find out. But in the second case, here the reaction enthalpy and reaction entropy both are dependent upon temperature. And what is the final expression? The final expression looks a bit tricky, and that is solved using mathematical programs. Then, so this is all about Van't Hoff's equation. Then we will go to the reaction gives energy at standard state. So if we know reaction gives energy at standard state, we can find out equilibrium constant, because it is a simple relation minus RT ln K. So by any means, if we know this one, then we can find out equilibrium constant. So what are the methods? So this reaction gives energy at standard state is an important parameter, and people are very much interested in determining this parameter. Okay, so in chemical equilibrium, the reaction free energy or reaction gives energy at standard state is an important parameter, and that can be obtained in three ways. Suppose by the first method is, suppose we know the equilibrium constant value for a particular reaction. If we know the equilibrium constant value, then using the expression minus RT ln K, we can find out reaction gives energy at standard state. That is the first method or first procedure to obtain delta R G0. The second procedure to obtain delta R G0 is using the formula delta R H0 minus T delta R S0. If we use this formula, we can also find out the reaction gives energy at standard state. But when we can use this formula? When we know the enthalpy data and entropy data. The enthalpy data is calculated either using a calorimeter or from spectroscopic experiments. Again, I am repeating, the enthalpy data can be obtained using calorimeter, or for some simple reactions it can be obtained using spectroscopic data also, like fluorescence spectroscopy and all. Similarly, the entropy data, the reaction entropy data is obtained from statistical thermodynamics. Again, that is not in the scope of this lecture, so I'll skip that. So this is the second method to determine the reaction gives energy at standard state. The third method is for gas reaction. The reaction gives energy at standard state can be obtained using statistical mechanics, and some molecular information is obtained from spectroscopic data as well. So delta R G0 or reaction Gibbs energy at standard state can be obtained in three ways. The first way is to use the expression minus RTLNK. That is, if you know the equilibrium constant, you can find out reaction Gibbs energy at standard state. Second procedure is to use the expression H minus T delta S. Here the enthalpy and entropy data needs to be known, and how the enthalpy data can be obtained from spectroscopic information or calorimetric information, calorimetric values, and the entropy data is obtained from statistical thermodynamics. Similarly, in the third way of determining the reaction Gibbs energy at standard state is using statistical mechanics and some spectroscopic data as well. So the method 2 and method 3 help in finding equilibrium constant of a reaction that are not studied in lab. So if we can find out delta R G0 or reaction Gibbs energy at standard state for a reaction, again I am repeating, if we can find out the reaction Gibbs energy at standard state for a reaction, we can find out equilibrium constant by using this expression, the first expression. So this delta R G0 is very important parameter, and if we can obtain this delta R G0 using the method 2 and method 3, we can find out the equilibrium constant of a reaction without doing that reaction in laboratory. So from if we can somehow manipulate the previous known data, some mathematical rearrangements and all those things, if we can do, and we can obtain the delta R G0 value for a particular reaction, then we can find out the equilibrium constant of the reaction even before performing the reaction. So tabulation of delta R G0 values or tabulation of the reaction Gibbs energy data at standard state is important. Okay, but generally the reaction Gibbs energy at standard state data are not tabulated, rather the formation of Gibbs energy of formation data is tabulated, because the reaction Gibbs energy is related to the Gibbs energy of formation at standard state by the expression we know that the reaction Gibbs energy at standard state is related to the Gibbs energy of formation. Okay, so with its summation expression, so generally the Gibbs energy of formation of any compound or any element is tabulated. Any compound, if we found a new compound, generally that Gibbs energy of formation of that compound is tabulated, and from that formation data we get the reaction Gibbs energy data, and from this reaction Gibbs energy data we get the equilibrium constant of the particular reaction. The standard Gibbs energy, it is important to note that the standard Gibbs energy of formation of elements in their standard reference states are 0 at all temperature. Again, this formation data we have to tabulate, but for elements like bromine in liquid state, it is its natural state. So again, that those natural states are chosen as reference states. So we have to choose a reference state, then only we can find out the difference. We cannot find out the absolute values. So those reference states are the natural states of the elements. Okay, like bromine in liquid state, as I said. So this is all about the reaction Gibbs energy at standard state. This is a very important parameter in chemical equilibrium. If we know this parameter, then we can find out equilibrium constant. And how do you know this parameter? This parameter is not tabulated, rather a different parameter, that is the Gibbs energy of formation of compounds are tabulated, because if we know the formation, then we can find out the reaction Gibbs energy. So this is all about the reaction Gibbs energy at standard state and why it is important. Now we will discuss what is the effect of nature of reaction on Gibbs reaction gives energy at standard state. Nature of reaction means suppose it is exothermic reaction, endothermic reaction, and what is the effect of temperature and all those on the reaction gives energy at standard state. So reaction gives energy at standard state is equal to enthalpy minus T delta S. Okay, so what will happen to reaction gives energy for a exothermic reaction? Mostly for exothermic reaction, the enthalpy value will be negative. So this enthalpy value is negative. T delta S is also negative. So two negative terms will give a further negative term. So total RHS become negative. Now this delta R G0 or gives reaction gives energy is also negative. Now reaction gives energy is negative means what? The process will be spontaneous. From thermodynamics we know that gives energy is negative means the process will be spontaneous. So for exothermic reaction, the value of equilibrium constant will become more than 1 because delta R G0 is equal to minus RT ln K. So if this delta R G0 is negative, so K will be more than 1 means the reaction will proceed towards forward direction. Now what will happen to the endothermic reaction? Endothermic reaction means this delta R H0 will be positive. Now in RHS there are two terms, one term is positive and the second term is negative. So the reaction will proceed only when this total term is negative. When the change in free energy is negative, then only the reaction will proceed. So for endothermic reaction, this T delta S term should overcome the magnitude of the enthalpy term, and that can be done in two ways. Either you increase the entropy or you increase the temperature. Suppose let's consider the first case. So by increasing entropy for gaseous reaction, if more number of gaseous products are forming, then the number of reactants, that means the entropy of the system is increasing. For such a case, this second term will supersede the first term and the overall term will be negative and the equilibrium constant will be more than 1 and the reaction will go towards product side or reaction will go towards completion. Again I am repeating it, if entropy is in more, then this equilibrium constant will be more than 1 or the reaction will go towards forward direction. And how do you know that entropy is dominating? The simple way is to judge the number of gaseous molecules. If the number of gaseous molecules in the product side is more than the number of gaseous molecules in the reactant side, that means entropy of the system is increasing. And the second way of increasing this second term is at high temperature. If the temperature is more, then the second term will dominate the first term and eventually the total term will be negative and the equilibrium constant will be more than 1 and the reaction will proceed towards product formation or proceed in a forward direction. So when the reaction will proceed in a forward direction or when the equilibrium constant will be more than 1, there are three cases. For exothermic reaction, it will inherently be more than 1, the equilibrium constant will be more than 1 and the reaction will proceed towards product formation. The second case is when the entropy of the reaction increases. When entropy of the system increases as a cause of the reaction, when entropy of the system increases, the equilibrium constant will be more and the reaction will proceed towards product formation. The third case is at high temperature. At high temperature also the equilibrium will shift towards product formation. So with this we'll stop here. Next class, next session we'll discuss free energy of mixing and spontaneity, and we'll also study an important, we'll also try to understand an important concept, why gaseous reaction never go to completion.